In the last video we developed the trapezoid rule, a way of approximating definite integrals, or better known as a numerical integration technique. And trapezoid is an improvement upon the rectangles. Instead, we use these trapezoids, right, to approximate the area under the curve. So it does a little bit better job, you would think. And so let's just do an actual calculation of this. Here's the rule we developed from the last video, and we're going to use the trapezoid rule now to approximate this integral here. And so this is the same integral we were looking at in the last video, and I'm going to stick with n equal 5 here again. So the delta x is going to be the same, b minus a divided by n, which is 5, so this is 1/5 again, or 2/10. Now, again, our endpoints of our subintervals, we divide the length from 0 to 1 into 5 equally spaced subintervals. And so, of course, the first one starts at 0, and then the next one is delta x away, so 0 plus that is 0.2, and so on. This is the same that we had in the last example, where we were using the midpoint rule. And so what do we have here, right? So remember what the notation means here, the y sub 0, the y sub 1, and so on. So what is y sub 0? Let's just say y sub 0 is f of x sub 0, which in this case would be f of 0. And of course the function, right, is the integrand. Okay. So in this case f of 0 would just be what? E to the, if I plug in x is 0, this whole exponent is just 0, e to the 0, which is actually 1. I mean, so you can actually evaluate that one. And then y sub 1 would be f of x sub 1. I'm not going to, f of 0.2, right? And so on, right, all the way down to y sub n is f of x sub n, which in this case, well, x sub n is x sub 5. Let's just go ahead and put it in our, which is f of 1. And I can go and I'll go and plug in 1. If I plug in 1, I get 1 squared is 1, 1/2, negative 0.5, so I get e to negative 0.5. Okay. But again, I'm going to use my calculator to do all this, but I would like you to show the setup, which is basically, right, this thing right here, right, plugging in those values. And so let's do that. Let's see what that's going to look like. Okay. So t sub 5, the trapezoid rule approximation with n equal 5 is, right, delta x divided by 2, and we've already found delta x to be 0.2, so delta x 0.2 divided by 2, of course that's going to be 0.1. And then notice again, we talked about the coefficient pattern that's developed with the trapezoid rule, right? So it's y sub 0 plus 2y sub 1 plus 2y sub 2 plus 2y sub n minus 1, and then 1y sub n. So the first and the last have a coefficient of 1. Okay. So this will be y sub 0, and we know y sub 0 is equal to 1, but I'm just going to write this as y sub 0 plus 2y sub 1 plus 2y sub 2 plus 2y sub 3 plus 2y sub 4 plus y sub 5. Okay. So, again, if I'm plugging in y sub 0, we already said was equal to 1. 2 times y sub 1 will be 2 times e to the negative x squared, where x is 0.2. Right. And so on, right? So we can fill in all the rest of those. So there it is. I'd like you to set that up, and then what is the approximation then? So you should give all your endpoints, so we know you know what those are. Don't just copy down the formula and then use a program to find the value of the trapezoid rule. All right. I'm just going to edit. If you remember in the last video, I had this was from the midpoint rule, so I'm just going to edit this. And so what I'm going to do is I'm going to do second entry, and I'm just going to edit this thing. It was 0.2 divided by 0.2 divided by 2 is just 0.1, right? And then it was 1, and I'm just going to insert. I'm just going to insert 1 because I know that's going to be 1. Y sub 0 was 1. It's e to the 0. I mean, right, if I want to plug it in, but I'm just going to simplify that. But then this one I'm going to have to plug in, right? So plus 2. Okay, so I insert the 2 there. E to the negative, and what do I need that to be? Negative 0.2. 0.2, right? And notice how I've got it set up. I got the parentheses on that exponent. Negative 0.2 squared divided by 2, and then you can see on the next line is my closed parentheses. Okay. Then the next one will be 2y sub 2, so I need to insert, and when I'm inserting, if you don't know, second INS will change your cursor to the underscore, where I can edit that. 2 times e, and this time, what's the y sub 2? It's f of x sub 2, which is 0.4. So I need that to be 0.4. And then second insert again, I need a 2. Y sub 3, which is 0.6. And then so on. 0.8 for x sub 4. And then the last one is just e to the negative 0.5, and so I'll just enter that negative 0.5 and delete all this. So I went ahead and calculated that. Okay. So there, hopefully. And again, this is where the big mistakes are made, so you just might want to double check and make sure that you've got everything. So 0.1 times, I open the parentheses there, 1 plus 2 times e to the 0.2 squared. 2 times e to the 0.4, negative 0.4 squared divided by 2, plus 2 times 0.6, 2 times point, see the point there, 8, and then plus e to the, and this was when x sub 5 was equal to 1, and so I get e to the negative, right, 1 squared divided by 2, as we said down here, and e to the negative 0.5 for that one. All right, so I can do it all in one step, and there is my result. So I'll just round that off. All right, all those 9s, I'll just round it off to 0.8536. 0.8536. Okay. But again, it's not just give this answer. You will have to show that you understand all these parts and how this is set up. Okay, because there's too many numerical integration calculators out there that will just give you the answer. We don't want you to be button pushers. We want you to understand the algorithm and how to program that. Now, so that's just the calculation. So it's pretty easy, but just be careful with entering it into your calculator. So this trapezoid rule then is pretty nice. So notice the progression. We started with rectangles, which was basically horizontal lines, or you can think about them as linear equations, but they're degree 0 polynomials, right? Constant functions. These now have lines segments at the top that have some non-zero slope, right? These line segments have slope, so they're like a degree 1 polynomial. So we started with degree 0 polynomial, degree 1, what's the next step? Degree 2. Okay, so if we go to degree 2, then it gets a little bit more complicated in the derivation, and I'm not going to go through that in here. But in this case, if I have, subintervals, I'm going to need, actually, in order to make this work, I'm going to need two subintervals. So here's two arbitrary subintervals, x sub I minus 1, x sub I, x sub I plus 1. And so if we have some function up here, right, what we're going to do is actually try and fit through these 3 points here. We're going to try and fit a quadratic function, right? A quadratic function. And that quadratic function might look, something like that, right? A parabola opening downward, maybe if I continue it on, it looks like that. But, obviously outside of this panel, it begins to look really bad from the function, the green curve versus the purple curve. But right in here, right, it does a pretty good job. A little bit, a little bit off here, but it does a pretty good job of approximating. And the problem is, though, a couple things about this method. It's the derivation of it is a little bit harder, and I'm not going to go into it. But I will note that in order to get a parabola, we need to get a distinct parabola, we need 3 different points. And so these 3 points, right, will define a unique degree 2 function, a parabola. Okay, and based on that, right, we can do a calculation and we can get what is known as Simpsons Rule. So I'm going to show you Simpsons Rule right now. This was the Trapezoid Rule. So Simpsons Rule looks like this. Simpsons Rule looks like this. And notice the midpoint rule, we just had delta x. Simpsons Rule, we had delta x divided by 2, and then Simpsons Rule, delta x divided by 3. Kind of a change there, kind of a little increment there, makes sense. And then, when we look at the contributions to these, remember y sub 0, again, y sub 0 again is f of x sub 0. Keep that in mind, those are the same. Y sub 1 is f of x sub 1, and so on. Okay? All the way down to y sub n. Right? And you see, this is the Simpsons Rule, and again, if I went through the derivation, you would understand where these came from, but it's kind of a pattern. See the coefficient pattern? It starts with 1, like it did for the Trapezoid Rule, and then it jumps to 4, and then 2, and then 4, and then 2, and then 4, and then 2. It keeps alternating between 4 and 2, 4 and 2, 4 and 2, until the very end it goes 2, 4, and then the last one is 1. So it's got this pattern to it. Okay? But this is the Simpsons Rule. And this pattern basically comes from the fact that, if this say is the x sub 0, let's just say this is x sub 0, x sub 1, x sub 2, your first sort of what we say panels, you got two panels here, two subintervals here to work with. The next time we do something, then the next panel, the next three things, we're going to use this one again, right? Going to use this one again, and so there's something about that using that causes this coefficient pattern to happen. And again, without deriving the Simpsons Rule for you, it is a little mysterious where these come from. But again, I can show that maybe in a separate video. As maybe I'll tack that on as a extra credit sort of thing to take a look at if you're interested. Okay, but now that we have Simpsons Rule, this is going to be used. One thing I'll have you note, though, you say let's use Simpsons Rule to approximate this with n equals 6. You say, well, let's use n equal 5. Problem with this is this pattern and this method requires you to have an even number of subdivision, right? And that's stressed here. And so unlike the previous two, the midpoint and trapezoid rule, Simpsons Rule needs an even number. And so let's take a look at this problem here with Simpsons Rule. So delta x is what from 1 minus 0 over 2. That's the same, right? Oh, sorry, over 2, over 6. That's not the same, actually, than what we had. It's 1/6. Okay. And what are our endpoints of our subintervals? X of 0 is 0. X of 1 is 1/6. Okay. And now 1/6, I'm not going to write that as a decimal. I'm going to leave that exact. X of 2 is, add 1/6 to 1/6, 2/6. 2/6 is 1/3. X of 3 is 3/6. What is 3/6? 1/2. X of 4 is 4/6 or 2/3. X of 5 is 5/6. And x of 6 is 6/6 or 1, which is where we should be. We should end at 1. Right? So just stepping off by 1/6 each time we get these values. Okay. And so Simpsons Rule, right, is what? Delta x divided by 3. So that's 1/6 divided by 3. And it's going to be y sub 0 plus 4y sub 1 plus 2y sub 2 plus 4y sub 3 plus 2y sub 4 plus 4y sub 5 plus y sub 6. And notice the pattern. It's 1, 4, 2, 4, 2, 4, 1. That's that pattern we were talking about. Okay. Now again, our function's the same, So, for instance, let's see, 4y sub 1 would be 4 times f of x of 1, which is equal to 4 times f of what? 1/6. That's x of 1. Right? So this would be 4e to the negative 1/6 squared divided by 2. So it gets a little messy in there, right, with what we're doing, so we're going to be real careful on our calculator to make sure we're careful in evaluating that. Okay. I also note that 1/6 divided by 3 is 1/18. Right, dividing by 3 is the same as multiplying by 1/3. So in the calculator, let's see if we can get this. Oops, I don't want to use that one. We'll use this one again. Okay. I'm going to reuse. I'm just going to edit the one I have, and I'm going to do that by second entry. Second, and hit the enter button for entry. That recopies what you have there. And so go to the front. I've got 1/18. 1 divided by, I'm going to have to insert 18. I like to put parentheses around that. Whoops. So there's my 1/18. Okay, 1/18 times, and then I've got my y sub 0, which is just going to be, right, e to the what? E to the 0 power, which is 1. So I'm going to leave that at 1. Right, that's the y sub 0. 4 times y sub 1, and we've got that here. Right. So that's going to be a 4 e raised to the negative, and here I had a decimal point 6. Now I'm going to do the actual fraction. I don't want to round that off, so I'm going to do 1 and insert divided by 6, close parentheses. So it's getting a little crazy, right? But I've got that 1/6. Notice that 1/6 is in the parentheses. Don't bring the negative sign inside of it, right? The negative sign is not inside the parentheses. So just to emphasize, hopefully you recognize that when I look at negative x squared, That is not the same thing as negative x quantity squared, which, by the way, would just be positive x squared, right? So this negative is, you'll do the squaring first and then multiply by -1. That's what we have there. So be careful. That has to be, right, the negative sign has to be outside of that, what you're squaring. Okay? And then 2y sub 2, where x sub 2 is 1/3. So I've got plus 2, there we go, e to the negative, and now I'm going to put in 1/3. So I've got a 1, and I need to insert divided by 3, close the parentheses, squared. So I'm just sort of inserting that in, divided by 2. Again, notice my negative sign, I'll move the cursor up to that, is outside that particular parentheses. So I've got nested parentheses. I've got parentheses around the 1/3. So I do the 1 divided by 3, right, first, square that. Then I multiply by -1, divide by 2. And you see the parentheses opening there and closing here. Then I will evaluate e to that power. So that's the way you want the calculator to do it. Okay. Plus 4y sub 3, so there's a 4. E to the negative, and y sub 3 is f of x sub 3, which is 1/2. So here I won't worry about a fraction. I can put that as a decimal because that's exact. Right? Whereas 1/3 would be 0.333333. I can't do that in the calculator, so I'll leave that. That's why I left that as 1/3. But 0.5. Okay, and then 2 y sub 4. Y sub 4 is 2/3. So 2e to the negative. Here I'll need a parentheses. 2 divided by 3. Insert that, divided by 3, close the parentheses, right? So that's squared, divided by 2, right? And then plus 4 y sub 5. So here I'm going to have to insert a 4. And y sub 5 is 5/6. So that's going to be e to the negative 5/6 squared, divided by 2, close the parentheses on the exponent. Okay, and I've got one more to do. Of course, why do I have one more when I was copying it? Because we went from n equals 5 to n equals 6. And then x sub 6 is just going to be 1. So it's 1, notice the coefficient is 1, so plus just e. And if I plug in 1, right, to this, what do we get? E to the negative, what? 1/2 power. And I really didn't need to put this in parentheses, but I did. Okay. So if I did that all correctly, if there's a possible I can make a mistake in that, obviously there's a lot going on, so you want to double check and make sure that everything is correct, right? I got the 1/18th, got the y sub 0, which we know came out to be 1, right? So plug in 0, e to the 0 is 1. I've got this one 4 times in 1/6, and then 2, right? y2 is 1/3, so the 1/3 there, and then 4, that's a half for y sub 3, and then 2, 2/3, and then coefficient 4, 5/6, and then finally the coefficient of 1. And plugging in x equal 1 gave me 1/2, negative 1/2 for the exponent. All right. So with the calculation I got was 0.8556. We'll round it off to. So that's the calculation. Right. So again, this integral that we've been doing in 3 different ways has no way to be done using the fundamental theorem of calculus as a finite, trying to estimate with a finite number of functions. The antiderivative doesn't exist as that, so the numerical methods are good. The idea being that the Simpsons rule in general would generally give you a better approximation for the same number of subintervals as, say, the trapezoid rule. It's a little more computation involved in it, but as far as programming it, then you can, we've chugged through with n equals 6. It would get obviously hard if you did n equal 20, n equal 100, n equal 200. Obviously, you're not going to do that manually, but you can get a better and better approximation. I want to just close with an example of an integral we can do, and that is this one here, the integral from 1 to 2 of 3 divided by x. Right? The exact value can be done because I know the antiderivative of 3 divided by x is 3 times the natural log of x. Well, natural log of the absolute value of x, but of course, look at our range, we're only positive, so I'll just leave it natural log of x. So I plug in at 2 and I plug in at 1, natural log of 1 is 0, so I just get 3 times the natural log of 2. Now, to 8 decimal places, if I use my calculator, 3 natural log of 2 is equal to this. Okay? So now what I just do is I've showed you here, I've done these calculations with my own numerical methods calculator, basically. But if you were to evaluate this integral here using the midpoint rule, trapezoid rule, or Simpsons rule with n equal 4, 6, 10, and 20, you can see the calculations. And here's the exact value. By the time I get to n equal 20, the midpoint rule is accurate to the third decimal place. Right, see that? Accurate to the third decimal place. Then we get a 2 here, and we're off. For trapezoid rule, accurate to third decimal place. For Simpsons rule, notice we're accurate to the 5th decimal place. So again, as I was saying, the Simpsons rule generally will converge more rapidly to the actual value than the trapezoid rule. Now, depending on your application or situation, how accurate do you need to be to the estimate of this definite integral? I mean, if you're using the Simpsons rule for n equal 20, you're accurate already to the 5th decimal place. What accuracy do you need? If you only need to go to, say the 3rd decimal place, we're almost accurate with the Simpsons rule with n equal 4. So we can converge pretty accurately to the actual value of the definite integral. So numerical methods are real important. These are very easy for you if you're a computer science person to program these in, and I would encourage you to do that if you're a programmer. Write a program that will calculate the midpoint, trapezoid, and Simpsons rule for different values of n. Just have it where you input the value of n, input the function, and I encourage you to do that. It would be a good exercise. Okay.